Welcome to the course on Game Theory in the autumn term 2020 at the University Mannheim. This is the second video of week 9. So in the last video we started with section 5.3 on extensive games without perfect information. We saw the notion of perfect recall. And now it might be time to go to examples, but I will not. In the rest of this section, we will not see any instructive examples. Some toy games will come in the exercises, and some typical real games which can be seen as extensive games without perfect information are card games, where nature gives each player some cards and the player knows only his own cards, not the cards of the other people. For example, Skat is such a game. Also games where several players move simultaneously can be modeled as extensive games without perfect information. So in the rest of this section, I will define three notions of strategies. First, definition 5.9 will be generalized in the case of player 0 having not too much to do, only finitely many plays. We will also define utility functions for these strategies. So we will get again associated games in normal form. And then I will define in definition 5.28 mixed strategies, or I will consider mixed strategies and define something else, some probabilities. In definition 5.29 I will come to so-called behavior strategies. And theorem 5.30 will then explain the relations between mixed strategies and behavior strategies. Both are generalizations of pure strategies, of the strategies of 5.27, and the behavior strategies are much easier to deal with. The spaces of behavior strategies are much smaller than the spaces of mixed strategies. But in the theorem 5.30 we'll tell that they are closely related, and it will allow us to get results for behavior strategies from results for mixed strategies and vice versa. So that's the program for this in the next video and the rest of this section 5.3. So one could also define subgames and subgame perfect equilibria, but I will not, because the backward induction does not work well in this case of imperfect information. And also the theorem 5.14 on backward induction does not hold here. So, but the mixed strategies are useful because we have strong results about them. We have existence of Nash equilibria for mixed extensions of finite games. And then we can, by theorem 5.30, translate this also to results for behavior strategies. So first now I somehow generalize the definition 5.9 on strategies for extensive games. So now gamma is again such a 7-tuple, an extensive game with or without chance moves and without perfect information. So what I called strategy before is now called pure strategy, because we will also consider mixed strategies and behavior strategies. So it is defined essentially as before in 5.9, a pure strategy of player I, who may be player nature or some person player, is a map which associates to each play where player I has to do the next move, a possible move. So I want that for the move is possible, that's written here. So I want that the move is possible. And also because we have imperfect information, we have to demand that the same move is prescribed by the strategy for all plays in the same information set. So that's written here. So if you have two plays alpha and alpha tilde in the same information set, player I does not know where he is, whether in alpha or alpha tilde, therefore his strategy can only prescribe the same move for these plays. So the set of all strategies of player I is then again called S upper index I, and S is again the product of S1 to Sm. Here I do not have S0 in the product. So now I can generalize the map better from definition 5.9 if I have any complete tuple of strategies, so some element of the tuple S0 times S, if player nature has something to do, or just in strategy combination in S, if player 0 has no role, then the map beta is defined as before. It gives for the strategy combination the unique final play which is reached after carrying out all the steps in the strategy combination, starting with an empty play. So let me try to go back to this slide. Here it is. So it is essentially it's the same definition as before. So it's an inductive definition. The final play which is reached by some complete strategy combination, including player 0 if he has to do something, it's just a sequence of moves which at each step are prescribed by the corresponding strategy of the player whose turn is it to make the next move. So it's an inductive definition and it works. So and the next definition also works. So suppose now that player 0 has not too much to do, that he has to do the next move only in a finite set of moves. That's this condition here. Then we obtain as here a utility function for the person player I on the set of strategy combinations of the person players. So if player 0 has nothing to do, we have of course here downstairs in this situation here. Here. But if player 0 has to do play a role, we have to take a weighted sum over these utility values over the possible final plays and over the possible strategies of player 0. So we have to take the sum over the strategies of player 0 with these probabilities, which I've written here, and which arise in the most natural way. So in that way, we now get a utility function here. So now I try to go back. So the map beta is defined as before. And for the person player UI, the utility function is also defined as before if the set of plays where player's nature has to do the next move is finite. And then we also get again an associated game in normal form. So maybe it's useful to stress that the map beta is well defined, although the players don't know in which play they are. So, but the players don't know, but the game knows. So the game always is in a fixed play and always some next move is done. Only the players do not know where the game is. The game itself somehow knows where it is and at which play it is. Therefore, this map beta is well defined, although we have imperfect information. So, and then the last part which I need here, which I did not need before in 5.9, is the following. Now a strategy SI of some player I, person player or nature, is called compatible with a given play if the player I somehow gives a correct contribution from his side to reach the play alpha. That means, here it's a condition here downstairs, if you have any play coming before alpha, such that it's the turn of player I to do the next move, then the next move towards play alpha must be the move which is prescribed by the strategy of player I. So player I does not make any mistakes. His moves turn towards the play alpha. So now one could formulate a little lemma. If we have a complete strategy combination for all players, then it is compatible with a given final play if and only if beta of the final play is, if beta of the strategy combination is the final play. So maybe I formulate a small lemma here. So this is given, and we have a strategy, find a play alpha. Then for any I in A with union with 0, Si is compatible with this alpha if and only if alpha is the final play which arises from S0 and S. So this is a rather obvious lemma. It illustrates this meaning of compatibility. If all the strategies do their part to arrive at this final play alpha, then this final play alpha is really the result of the strategy combination. So now I still give the next definition in this video, notion of mixed strategies. Now we have defined pure strategies. And so now we suppose we have a finite extensive game with or without chance moves and without perfect information. Then we do get an associated game in normal form from the last definition. This is well defined and this is also finite. And then we also get a mixed extension. So we do have a mixed extension here for the finite, for the associated game in normal form for a finite extensive game. And now I want to define some numbers which are will be parts of probabilities. So let me scroll down. At the in part D of this, in the last part C of this definition, I want to define some probability pi of G alpha. So here small g is a mixed strategy combination, and alpha is any possible play in our game tree. And I want a probability pi of G alpha, which says that alpha is reached if we play the mixed strategy combination G. And you see this will be a product of some other numbers, some numbers for each of the players. So for player nature, it will depend only on alpha, not on G. But for the other players, it will depend on their own part of the mixed strategy and the play alpha. So that's what I want to define in part C. And now I have to carry out the definitions of the parts for the person players and the part for the player nature. Here's the part for the person players. So I will define it for any person player I will define a pi upper index I from the set of mixed strategies of player I times the set of plays 2, 0, 1. And yeah, it is defined by the formula which you see. Here I have introduced the notations. The set of pure strategies of player I is here enumerated by Si1 to SINI. So Ni is the numbers of pure strategies of player I, and Gi is in the corresponding mixed strategy. The coefficients are called gamma ij. So the coefficients give us a probability distribution over this set Si of pure strategies. And then the part of the probability pi I of Gi alpha is just the sum of those probabilities which describe pure strategies of player I which are compatible with alpha. So the probability with the part of player I of a probability for the play alpha is the sum of the probabilities of those pure strategies in the mixed strategy which are compatible with alpha. So this makes sense. Now for the player nature, for the player 0, we have already some probability distribution over for each play where it's the turn of player 0 to do something. We have a probability distribution W beta or W alpha on the possible moves after this play alpha. So in here now we have a fixed play alpha, not belonging to player 0, and the part of the probability for player 0 to reach this play alpha is now the product over all the probabilities that he chooses the correct move in the earlier place where it's his turn to do the next move. So we have the play alpha, and before we have a number of other plays, and in some of these plays it's the turn of player 0, player nature, to do the next move. And he has to do the correct move, he has to do the compatible move. And the product of the probabilities for these compatible moves is now the number which is a part of the probability of player 0 for alpha, so pi 0 of alpha, which is also a natural condition. So now we see we can put this together, and then we get this map pi from G times B, which gives them for each play the probability that it is reached by the mixed strategy combination G. And again, one can formulate a lemma. If I restrict this to the final plays, so maybe I try to write again the lemma here. I fix now G, and then this pi of G dot from F to 0, 1 is a probability distribution on F. So I get a probability for each play, but yeah, on the set of all plays it's not a probability distribution. But on the set of final plays, this gives us indeed a probability distribution over the final plays, because one of them is reached, but only one of them is reached. They exclude one another. Therefore, this must give a probability distribution. You see, I just formulated this lemma. I didn't write it up in the manuscript, and I also have no exercise for it, but it must be true. So I will not prove it right now. So at this point I want to stop, else the video will be too long, but I will continue in the next video with the third notion of strategies, the behavior strategies. Thank you very much.